Welcome back to BE 110. Today we're going to begin deriving the conservation laws for continua by deriving the conservation of mass. Now there are actually two versions of conservation of mass for a continuum. They represent the same physical principle, but one of them is a Lagrangian form, so mass conservation as seen by a material observer, and the other is an Eulerian form, mass conservation as seen by a fixed spatial observer. So first we'll derive the Lagrangian form of mass conservation, and to do that we'll consider a deforming body with a motion described using a Lagrangian material representation as little x equals little x of big X and t. And from this we can get the components of the deformation gradient tensor FIR, being the partial derivatives of little xi with respect to big XR, Now, conservation of the mass contained within a closed material region R can then be expressed as follows. The triple integral over the region R of rho naught, the underformed density, with respect to volume in the underformed state, is equal to the triple integral over R of the deformed density with respect to the deformed volume dV, or writing this in components, the triple integral of rho naught, the underformed density, with respect to d big X1, d big X2, and d big X3 is equal to the triple integral over R of rho, the current density, d little x1, d little x2, d little x3. Now we need to convert deformed coordinates to underformed coordinates in our integral. And the way we do that is to use the partial derivatives in a chain rule, del xi, del xr, and in fact the expression that you get if you derive the conversion from d little x1, d little x2, and d little x3 to d big X1, d big X2, d big X3 is actually the determinant of del xi, del xr, and that's known as the volume integral Jacobian, and as you can see it's equal to the determinant of the deformation gradient. So therefore we can now write our integral equation as the triple integral over R of rho naught, the underformed density with respect to underformed coordinates dx1, dx2, dx3 is equal to the triple integral with respect to R of rho, the deformed density, times the determinant of f, d big X1, d big X2, d big X3. But here we observe that the region R is completely arbitrary. We could choose any and every region R, and this must still be valid. Therefore, the integrand itself, these terms here, must identically be satisfied, or the difference must be identically zero, which would therefore give us that rho naught must equal rho times the determinant of f. So that's our conservation of mass in the Lagrangian form, which we could also write as rho naught over rho, the underformed density over the deformed density equals the determinant of f, which is therefore equal to the deformed volume over the underformed volume. So this is the Lagrangian form of mass conservation for a continuum. To illustrate this, let's consider a unit cube whose sides are aligned with the principal axes of stretch. After the deformation, the sides would now have lengths lambda 1, lambda 2, and lambda 3, which are the three eigenvalues of the stretch tensor U. So they are the principal stretches. So here we see that in this diagram. The original unit cube now has dimensions lambda 1, lambda 2, and lambda 3. The determinant of F from the polar decomposition theorem is also the determinant of R times U, which equals the determinant of R times the determinant of U. Now, R is an orthogonal rotation tensor, and so its determinant is 1, meaning that the determinant of F must equal the determinant of U, which in this case would be the product of the principal stretches, lambda 1, lambda 2, lambda 3, which of course is the deformed volume of our original unit cube, which had undeformed volume of 1 by 1 by 1, and therefore the ratio of the deformed volume to the undeformed volume, lambda 1, lambda 2, lambda 3, is the determinant of F, as we expected. If a material is incompressible, that means its density is constant, and material volumes don't change, so rho is equal to rho naught, or d little v is equal to d big V. Therefore, conservation of mass states that the determinant of F equals 1 for an incompressible continuum. This is sometimes known as the kinematic incompressibility constraint. So if a continuum is incompressible, we can use this constraint to determine part of the stretch. For example, given lambda 1 and lambda 2 as principal stretches in an incompressible material, we can use the kinematic incompressibility constraint to show that lambda 3, the third principal stretch, must be 1 over lambda 1 times lambda 2. Now, next let's look at the case of an infinitesimal strain field and infinitesimal rotations, in other words, where the displacement gradients are small. So we'll expand the components of the deformation gradient tensor in terms of the displacement gradients. In other words, FIR equals del UI del XR plus delta IR. And therefore, the determinant of F will be the determinant of the following matrix: del U1 del X1 plus 1, del U1 del X2, del U1 del X3 in the first row, del U2 del X1, del U2 del X2 plus 1, and del U2 del X3 in the second row, and del U3 del X1, del U3 del X2, del U3 del X3 plus 1 in the third row. So the determinant of this matrix will be del U1 del X1 plus 1, this term here, times the determinant of this submatrix, which is del U2 del X2 plus 1, times del U3 del X3 plus 1, minus del U2 del X3 del U3 del X2, minus this term del U1 del X2 times the determinant of this submatrix, del U2 del X1 times del U3 del X3 plus 1, minus del U2 del X3 times del U3 del X1, plus del U1 del X3 times the determinant of this submatrix, del U2 del X1 times del U3 del X2, minus del U2 del X2 plus 1 times del U3 del X1. Now, if we look at this expression, we see that all of the terms here, 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 and here, all involve quadratic or higher combinations of these derivatives. So we get 1, this product there, plus del u1 del x1 plus del u2 del x2 plus del u3 del x3, plus a lot of terms that are all of order del ui del xr squared or smaller. So if del ui del xr is much less than 1, then terms of order del ui del xr squared and smaller are even less than 1, and so the determinant of f is approximately equal to 1 plus del ui del xi for small displacement gradients. Now remembering that the Cauchy strain tensor epsilon ij is del ui del xj plus del uj del xi divided by 2, you can see that del ui del xi is just EII, the trace of epsilon. So in other words, in the limit of infinitesimal strains and rotations, the determinant of f is 1 plus the trace of epsilon. The trace of epsilon will be 0 if there's no volume change, positive if it's greater than 0, negative if it's shrinking, and this term is called the dilatation. Let's do an exercise making use of the Lagrangian form of mass conservation. If a piece of lung tissue has an undeformed density of 0.8 grams per centimeter cubed and experiences the following Lagrangian strain field, what is the deformed density of the tissue? Is it A 0.6, B 0.7, C 0.8, D 0.9, or E 1.1? To do this, we first need to calculate C, the right Cauchy-Green deformation tensor, from E, the Green's strain tensor. And using C equals 2E plus I, we get that the components of C are 1.4, 0.1, 0, 0.1, 1.60, and 0, 0.6. That gives us that the determinant of C is 0.6 times the determinant of this block, which is 1.4 times 1.6 minus 0.1 squared, which is 1.338. Now the determinant of C is the determinant of F transpose F, which is the square of the determinant of F. Therefore, the determinant of F, which is the deformed to undeformed volume ratio, or the undeformed to deformed density ratio, is equal to the square root of 1.338, which is 1.157. Now, if rho naught is 8 grams per centimeter cubed, therefore rho is 0.8 divided by 1.157, which is approximately equal to 0.7, which is choice B.